my name is Arnaud de Grandmaison, and it's my pleasure to moderate this Q&A session for the SRC for this LLVM developer meeting. So first of all, I have to say that I am very happy to see the success of this competition this year. We've had great presentations. This is an event I've been pushing in the LLVM community for many years with a number of other people. And to see that we have such a great edition for this year US LLVM meeting is really a good thing. So congratulations to all of you. You made a great job here. The second point I want to make before we dive into the questions is that this is a competition, so there should be a winner. So please vote. Voting is important. Normally you have received an email from Tanya with a link so that it's easy to vote. And in the event that you did not get this email, you can go in the WOVA, to the WOVA app in the navigation pane. There is a polls section, and there you will find the place where you can vote. Okay, now let's move on to the question. So the first question is regarding guided linking. Can you enforce the developer-specified constraints at runtime or load time?
So we don't actually have anything like that implemented yet. So if there's a constraint violation when you run the program, you'll probably get a crash. In certain cases, you could actually get incorrect behavior. We do know how we could check those constraints by adding some code when any library is loaded, and maybe some code that's run whenever you call DLOpen or DLSim. So we just need to, and implementing that is sort of a top priority for making it actually usable in practice. If we do detect that one of the constraints is violated, pretty much the only thing we can do is print an error message and crash the program, because there's no way to sort of restore the correct behavior after all the optimizations we've done for guided linking. So I hope that answers the question.
Okay, thanks, Sean. The next question is regarding enzyme. Have you considered lifting to LLVM IR and using binary rewriting to overcome the limitations related to having or not access to the IR, for example, in the case of library functions or JIT compilation or even self-modifying code?
So the answer is yes, but with a couple of caveats, namely, once we're able to get LLVM IR from whatever mechanism, be it from raising it from a lower level like assembly that was previously created from a different mechanism, we have to be able to go and run it through. And specifically, we have to be able to statically analyze a lot of this information about types. When you naturally go to a lower level like assembly, some of this information may be lost, and thus it may not be possible to statically analyze some of this. So the way that we've really been exploring here is not as much through binary rewriting and lifting, but more so from the use of fat libraries, that when you compile it alongside the actual binary itself includes the LLVM IR for it. Specifically as well on the topic of JIT compilation, we've also included enzyme in a package for Julia, a JIT that goes down to LLVM, and by effectively calling back and forth between the Julia higher level JIT as well as enzyme, we're able to automatically generate the requisite code that's necessary without having to do a raise from an even lower level up to LLVM. So in practice, it should be possible for relatively well-behaved codes. Of course, if you go and DLOpen some arbitrary piece of code, we can't statically analyze that per se. But if we are able to statically analyze the code that comes from the lower level, it should work. However, again, the default should always be to try to bring in the LLVM from a different level.
Thanks, William. The next question is, so we are back to guided linking. So did you use some sort of JIT to compile and optimize the functions from plugins and libraries when it was called for the first time?
Right, so I think this question might be based on a sort of misconception of how guided linking works. So we take all of the plugins and libraries at compile time and combine them all into normal dynamic libraries and dynamic programs, and there's no actual JIT or no actual new code being invoked at runtime. It's all a compile time optimization, essentially.
Okay, thank you. Now I have one question regarding spam. So can you say a few words about the prototyping platform that you have been using?
Sure. So our current prototype is implemented on x86-64, so we run it on real machines. But in terms of the hardware that we're looking at for the future work, we're targeting RISC-V at the moment.
Okay. And have you looked into the impact on the cache and the memory traffic with the memory hierarchy? Because basically you are just shuffling bytes a bit everywhere. So what is the impact there, and what is the impact on power as well?
Yeah, so this is something that now we're going to be looking at more closely once we have the hardware implementation on RISC-V. So this is not something that we currently have data on, but we'll have in the near future.
I would like also to say that at the moment, we are limiting the permutation granularity to 128 bytes. So in order to not to mess up with the last level cache locality, because on Intel x86 machines, the size of cache lines in last level caches is 128. So we do not permute data across different cache lines in order not to mess up with cache locality. But once we get to the hardware implementation, we can revisit this assumption as well.
Okay, thank you. We have another question for Enzyme. So how do you handle cases which are not differentiable for specific data values?
So there's a couple of different definitions for what you can mean by non-differentiable. So you can mean a non-differentiable instruction like, say, CPU ID, in which there is no reasonable notion of a derivative for it. These sort of non-differentiable instructions will be taken care of by activity analysis, which will go and run and say, this particular instruction does not impact the computation of the derivative, so we don't actually need to compute a derivative for it. The other way that you might imagine a function being non-differentiable is that we need more information to be able to ascertain exactly what that derivative is. There are several cases, for instance, where we need to ascertain exactly what type is stored in particular pieces of memory to choose the correct adjoint. And these sort of things will be handled with a compile time error saying, hi, we need more information about this particular piece of code. Can you provide it via metadata or the likes? The second mechanism that we have for this is that you can always specify a custom gradient for any particular piece of code or function, which one will be passed in via metadata. And instead of Enzyme automatically creating a gradient for that particular section of code, it will use whatever you specify.
Okay, thank you. One question on the approx tuner from Hashim. So how do you deal with systems that somehow don't support linearly the approximations, so that, for example, they become unstable, or there is some local instability? So that's akin to, let's say, local maximum or minimum, and that how do you overcome those issues?
Can you give a specific example, just so I better understand the scenario you're talking about?
So for example, in some simulations like n-body, so depending on the precision you have, your simulation might become unstable, and then if you have a higher precision, it becomes stable again. So, but there is a sweet spot in the middle where it is not so stable.
Absolutely. So basically, the tuning mechanism that we have expects some calibration data, right? And so you essentially have some calibration data which is representative of the data that you'll see in the wild, that you'll see in production, right? And if that data covers these cases where you know in some scenarios you need high precision, as you said, in some scenarios you need lower precision, that would be captured by the approximation tuning framework. But if you're talking about scenarios where the instability occurs in production, which was not captured in your representative calibration set, sure, that is a problem. There are ways to circumvent it, something that we currently don't implement, but if you essentially say periodically invoke a non-approximate version, and then you have your approximations running, you could sort of, match, and you see that, okay, now my approximate version is, tapering off, so you could reduce the level of approximation. Why this is relevant in our framework, if you've seen our talk, we have the ability to dynamically tune approximations. So that ability is there. If the thing that's lacking to deal the case that you specifically mentioned is that some ability to know that dynamically the input values that you saw are tapering off from your representative calibration set. So in theory, that is possible in our framework.
Okay.
Does that answer your question though?
Yeah, I think so. Then I have a question for Adel. So am I right if I sum up a bit bluntly that you don't actually do synthesis? You are rather massaging the source code that you are giving then to a synthesizer.
Can you repeat the question? Sorry, I didn't follow.
Yeah. So yes, my question is, am I right in my understanding that you don't actually do the synthesis yourself? You are massaging or preparing the source code so that the actual high-level synthesis tool can produce a good output.
Yes, that's correct. So we rely on the Intel OpenCL compiler to do the high-level synthesis and the hardware synthesis. And our compiler's goal is to, like you said, to produce an optimized version of the OpenCL kernels so that the HLS tool can generate good designs on the FPGA.
Okay. And what criteria have you used for selecting those 4 optimization passes? Where do they come from?
Right. So we have been the selection criteria that we use so far has been based on previous experiences with optimizing kernels in OpenCL, and also what Intel's best practices guide suggests in terms of manual transformations that the programmer can do to get better designs from their code. So we started with a case study where we tried to see how we can get a good performance on the camera pipeline benchmark that we used. Using hand-optimized OpenCL, and then we picked out we started looking at what are the optimizations that we thought are reasonable to be automated in the compiler, and those 4 were the ones that we started with, and then we are looking at other optimizations as well right now. So just to reiterate the question, basically we are more or less, we are looking at what are current optimization techniques that are known in the HLS community that have to be done by hand, and trying to select which ones can be automated in the compiler based on our compiler experiences.
Okay, thanks. It does answer my question, and I'm very happy to see and to have seen this talk because I have a hardware background, and every once in a while we have a talk about hardware synthesis and so on with LLVM. So that's interesting to see where it goes. I have one last question for Sean. So you, at some point in your presentation, you mentioned that Docker containers could be a good candidate for applying your guided linking. And I was a bit surprised not to see it in the future work. So why? Because I mean, it's definitely something which is very important those days.
Right. Well, basically, I had to cut down the future work section in the interest of time. It's definitely a very interesting direction for future work.
Okay, it's fair enough. Okay, so I think we are short of questions in the WOVA app. So would you have any questions here amongst the presenters that you would like to ask to each other on your presentations? So I will take silence as a no.
I do have one question from that someone sent me personally, but I can answer it here. So they're asking what the effect of guided linking is on link time. And basically the answer is that guided linking is fairly fast by itself, but you're creating this huge bitcode module that has a whole bunch of different programs and libraries in it, and running LTO on that is very slow for the usual reasons. So one other part of future work would be adding thin LTO support for this to hopefully speed that up.
Okay. Any other question? So I think then this will be the end of this Q&A session. Thanks a lot for your great presentation. That's lots of interesting work in many different directions, if not opposite, but widely different. And that's what is really great in these SRCs. I really like this part of the conference. So thanks a lot. And I hope to see you soon, maybe at the Euro LLVM for the next SRC. Bye.
Thank you so
Thanks,
much.
bye.
Thank you. Bye.